Hello, everyone. Welcome back. Today, I'm going to be talking about hypergeometric distributions. So, hypergeometric distributions, this is the probability model that describes the process whose repeated experiments are not independent. And that's the big difference here between hypergeometric distributions versus the distributions we previously did, like binomial and geometric. With both binomial and geometric, it was implied that the trials were independent. And so the outcome of one trial wouldn't affect the outcome of another trial. So, for example, things like rolling a die. If I roll a die, when I get a six this time, that doesn't mean I'm less likely to get a six next time because the die is tired of producing sixes, right? It doesn't work like that. Whereas, let's say I'm drawing marbles from an urn. If I replace them, then the trials are independent, right? Just because I got a purple marble this time doesn't mean I'm less likely to next time because I'm putting it back and I could draw it again or I could draw a different purple marble again with the same probability as before. However, let's say that I drew it and then I threw it away. Well, now I'm slightly less likely to get a purple marble the next time because one of them is gone, right? One of those outcomes is not available any longer. Or in the case that maybe all the purple marbles are gone, if I've drawn enough times that all of them are gone, well, now I have a 0% chance of drawing another one at a certain point as well, right? And so it's important to know what's what. Another example is, let's say we shuffle a deck of cards and I draw a card and then I put it back. Well, then I'm just as likely to draw the same card or a card with certain characteristics on it this time than I was last time. But if I draw a card, let's say it's a king, and then I throw it away, I put it to the side or I toss it away, and then I draw another card. Well, now I'm less likely to get a king because I already got one, and now there's only three kings left, and there's four of every other card left, and so I'm more likely to get some other card, than I am to get a king in comparison to before. Whereas before, every face value was equally likely to get, before I threw out that king. The same can be said about suits. Let's say it was the king of hearts specifically. Well, now I'm also slightly less likely to draw a heart because the king of one of the hearts is gone. I put it aside. And so now we have one less heart in our deck. And so that's the difference there. And so it's important to keep in mind that hypergeometric distribution is used during times when our trials are not independent, when they are dependent on one another. So here's an example. X represents the number of successes after n trials. So n is our number of trials. A is possible successes. And B is possible failures. So it's similar to the last two. The hypergeometric is similar to geometric and binomial in the sense that we have to define what's a success and what's a failure. Oh, and the expected value is going to be NA over A plus B. And that'll come in handy for us in a little bit as well. Okay, so let's move into example one. So example one says 5 cards are dealt from a deck of cards. What is the probability that the 5-card hand has 4 face cards? So right off the bat, we can kind of think about it and say, well, it's not that likely. We probably won't really get 5 face cards, right? But or 4 face cards. But let's see. Let's see how likely that is. So what would n be? N would be how many trials we're doing. We're doing 5 trials, right? We're shuffling our deck and we're drawing 5 cards, right? 5 cards are dealt from a deck of cards. A would be the number of possible successes. So what are face cards? Face cards are kings and queens and jacks. And there's 4 kings plus 4 queens plus 4 jacks. So in total, that is 12 possible successes. Now, how many successes do we desire out of those? We desire 4. We desire 4 face cards. So X would be 4. Oh, not B, sorry, 4. And then B is the possible failure. So how many cards are not face cards? Well, we know there's 52 cards total in the deck, right? We know there's 52 cards total in our deck. And 12 of them are face cards. So that means 40 of them are not non-face cards. So there's 40 failures, 40 non-face cards. So then I'm going to go kind of back up to here for a moment, and I'm going to find what is the probability of 4 successes in this case. It is going to be A choose X, right? We have 12 choose 4, right? We have 12 possible successes, and we're choosing 4 of them. And then we have 40 failures, and we're going to be choosing 1 of them, right? There's only 1 card left for our 5 cards, and that's going to be over A plus B, so 52, which is our total number of cards in our deck in all, and we're going to choose 5. And then if we plug all that into our calculator, we're going to get 0.0076 as our answer. But even leaving it like this would be acceptable for a lot of people. Even leaving it this way is acceptable to a lot of folks as well. Very good. So as you can see, it's less than a 1% chance. It's not all that likely. But that makes sense, right? How many face cards should we expect in a 5-card hand on average? Probably about 1 is my guess. But let's see. Let's see what the equation tells us. Well, the equation is going to be NA over A plus B. Oh. So that's going to be 5 times 12 over 12 plus 40, which is going to be 60 over 52, which is a little more than 1. Okay, so on average, we should expect about 1.15 cards, so about just over 1 card in a 5-card hand. And so given that, it makes sense why it's not all that likely that we're going to end up with 4, right? If the expected value is 1. Okay, let's try C. C asks, what is the probability that a 5-card hand has 4 aces? Okay, well, let's think about that for a moment. Well, how many possible successes are there? Well, there's 4, right? So A is 4. How many possible failures are there? Well, that would be the other 48 cards that are not those 4 aces, so 48, right? And what else? What else? How many trials are we doing? We're doing a 5-card hand, so N would be 5 because it's a 5-card hand, right? We're drawing 5 cards for our hand. And then X, what would X be? X would also be 4 because we want 4 successes. So the probability that we get 4 successes in this case, when a success is defined as getting an ace, that's going to be 4 choose 4, which actually is just going to be 1 because there's only one way to choose all 4 aces. And that's times 48 choose 1, right? Because there's 48 ways to choose the other card. Whatever it is, it's going to be something that's not an ace. And then that's going to be over 52 choose 5. And let's plug that into our calculator. And by the way, we should be expecting a very low probability here. What are the odds? Because even the odds of drawing face cards, 4 face cards was not all that great, right? And there were 12 face cards. There's only 4 aces. So what are the odds that we draw all 4 of them? That's only going to be 0.000018, right? So that's very, very small. That's much less than 1%. So if you ever draw, and by the way, if you ever draw 4 aces and get 4 of a kind aces, you probably won the hand. You probably won big money because this is very unlikely to actually happen. This is such a rare occurrence that doesn't happen every day. Very good. All right, let's try example 2. It's about deer, looks like. It says, a stomach parasite is being carried by a certain amount of deer on a conservation area. Of the 30 deer on the conservation, 8 are found to contain the parasite. 10 deer are removed and tested from the parasite. What is the probability that 5 of the 10 deer have the parasite? Okay, so let's in this case say that a success is having the parasite and a failure is not having the parasite. Now that might be a bit counterintuitive because we might think of a, wouldn't it be better if the deer didn't have the parasite? And yes, absolutely it would be. But for simplicity's sake, we are going to define a success as having the parasite, because that is what that's the language the question is using, of the probability of this many having it, right? And so it's going to be a little bit simpler that way. So in this case, what is n? Well, n is 10, right? Where our total number of deers that we're trialing is 10. What about our possible successes? Well, there's going to be 8, right? There's 8 that contain the parasite. So therefore, it's impossible, for example, for all 10 of the deer or 9 of the deer that we chose to have the parasite, because only 8 in the total population do. Then what about B? B is the other 22 deer that don't have the parasite. And then X would be 5, right? Because we want to know the probability that 5 deer out of these 30 deer have this parasite. So the probability of 5 successes, or 5 deer having the parasite, would be 8 choose 5 times 22 choose 5, right? Because we're getting 5 deer, doesn't matter the order, 5 deer from the 8 that do have the parasite, and also 22 deer of the, 5 of the 22 deer that don't have the parasite. And that's going to be over the total number of ways there are to choose 10 deer, which is going to be 30 choose 10. And that's going to end up being 0.049. So just shy of 5%. There's just shy of a 5% chance of exactly 5 of the 10 deer having the parasite. So not very likely, but it could happen. Next, we're wondering, what is the probability that 1 of the 10 deer have the parasite? Well, let's see. In this case, all our numbers are the same, except that X is going to be equal to 1, right? Because this time we're calculating for just one success, just one parasite-ridden deer, right? So in this case, we're going to do 8 choose 1. We want to figure out how many ways there are to choose one of the 8 deer with a parasite. And then the other 9 deer are going to come from the batch of deer of the 22 batch, the batch of 22 that don't have the parasite. Then here we have 30 choose 10, and it's going to be 0.13 as our answer. So that's going to be about 13%. So what that means to us is that 13% there's a 13% chance that if we do this, that exactly one deer will have the parasite, right? 13% chance that exactly one deer has the parasite. So we're more likely to have one deer having the parasite than 5, which makes sense if we think about it, right? If we consider the fact that, that only 8 of them out of 30 have this parasite. And so how many on average would we expect? Not a lot, right? Not 5 of them. And that's actually the next question, is how many deer should we expect within the 12 deer that were removed to have the parasite? I'm guessing they mean to have the parasite. Yeah, because they said they want to remove 10 deer are removed and tested from the parasite, that were removed to be tested for the parasite. Okay, so I think they explained that. So n is equal to 10 because there is 10 deer that were removed. A is equal to 8 and B is equal to 22, right? Same numbers as before. So our expected number of deer to have the parasite would be 10 times 8 over 30, which is 80 over 30, which is 2.67, right? So about 2 and 2/3. And that number is closer to 1 than it is to, oh no, that number is a bit closer to, no, that number is closer to 1 than it is to 5, right? It's 1.67 away from 1, and it's 2 1/3 away from 5, right? So it makes sense that 1 is going to have, the probability of 1 deer is going to be higher because we're a bit closer to that expected value there. So that makes sense. And by the way, I should mention that won't always be the case every time. There's some scenarios where it's going to be a little bit different from that, but in general, that's a pretty good indication. that the expected value, right, the value where we're going to have the highest individual probability is going to be closer in probability to things that are near it. Good. Okay. So that is it for hypergeometric distributions, and that's also it for this entire unit. The next unit, what's the next unit about? The next unit is about continuous probability distributions. So all of these ones that we did so far were discrete. So we'll talk about continuous ones next time. I'll also talk more about what that means. What is the difference between a continuous random variable versus a discrete one? But that is a lesson for another day. Either way, good work, everyone. Best of luck on your test, and we'll see you for Unit 5 and the final unit of this course. Good work, everyone, and goodbye.